So what's complex about fractions? Well, after we do a quick review of arithmetic fractions, we're going to see some bigger, more complicated problems like this. These are complex, but don't panic, they're not as bad as they look. We'll just take it easy and use all the rules you already know. What rules are those? Let's take a look and find out, and we'll start at the very beginning. A fraction is a ratio of two whole numbers, or of two groups of letters. And any fraction can be written in many different ways without changing its value. A very common type of problem asks us to reduce a fraction to its lowest terms, its simplest form, by factoring top and bottom and then dividing top and bottom by any common factors. The process is often called canceling. Another kind of problem goes in exactly the opposite direction. Find an equivalent fraction with a different denominator. For example, 3 over 4 equals what over 28? To solve that kind of problem, you want to find what was used to multiply the denominator. How did 4 become 28? It was multiplied by 7. And then do the same to the numerator. As usual, it's factoring that lets you examine exactly what's going on. Sometimes this kind of problem might look like this, and you'll have to start with something like that 3x that doesn't look like a fraction at all. But remember, 3x is really 3x over 1. You can write it as a fraction that way. And just as before, we want to find what was used to multiply the old denominator, in this case 1, to produce the new denominator, 2x plus 1. The answer? Surprise, 2x plus 1. So we multiply the numerator, 3x, by the same thing, 2x plus 1. And from there on, you would go ahead and use your distributive law. Multiplication and division of fractions was usually easy. Invert for division, reduce if you can, then multiply. For example, to divide by 4/9, invert it. Divide top and bottom by 4, and then by 3, and multiply out what's left. Addition or subtraction was a little more complicated. First, we need a least common denominator. Then we have to get the two denominators to be the same. That means we have to make equivalent fractions. 3 over 6x is the same as 1 over 2x. 4 over 6x is the same as 2 over 3x. Then we simply combine the numerators while keeping the new denominator unchanged. If that quick summary hasn't brought it all back to you, try reviewing the earlier modules on fractions. There are 2 separate ones which cover all of these processes. So that's all well and good, but what about complex fractions? What are they? Complex fractions are just expressions like these, where the numerator or denominator itself may contain fractions. Several layers of fractions, if you like. Our job is to simplify them to a tidier-looking fraction. So how do we work with a problem like this? There are 2 different methods. Method number 1, use your fraction rules, the ones we've just reviewed. Here, for example, the numerator is actually a subtraction of fractions problem. So, we work the problem. Find the LCD, 6, get 2 equivalent fractions, 3/6 and 2/6, and combine the 2 numerators. 3 minus 2 gives us 1/6. Simple. So let's do the same for the denominator. We have to rewrite 1 as a fraction with a denominator 5. So we write it as 5 over 5. Now it can be combined with the other fraction. 5 plus 2 gives us 7/5. And suddenly our problem has turned into a simple case of division of two fractions. And we know how to do that, don't we? Just invert and multiply, like this. So we've completed our problem by doing 2 addition problems and 1 division, one right after the other. These problems can be long, but you've already used each of the steps involved many times before. You may find that you like that way of handling complex fractions. Or you may find that you like this one better. Method number 2. When we're faced with a fraction we don't like, we often use multiplication to remove it. An idea. Perhaps we can do that here. Yes, perhaps we can. We multiply top and bottom of the big fraction by the same thing, in this case 3. And remember to use the distributive law so that every term gets multiplied. The extra layer of fractions just disappears in a puff of algebra. Exactly what we wanted. Try method number 2 now on the problem we did earlier. In this case, you want to get rid of fractions with denominators 2, 3, and 5. So the trick is to find the LCD of 2, 3, and 5, 30, and then multiply by that. Remember, we already know the answer is 5/42. See if you can get that answer by multiplying both top and bottom by 30. Well, here's what you wanted to get when you multiplied each term, top and bottom, by 30. And of course, we chose 30 in the first place because it was the LCD of 2, 3, and 5. Don't forget your standard order of operations here. Multiplication first and then addition. And one layer of fractions simply disappears when we simplify. That's really all there is to complex fractions, and you even have a choice of 2 different methods to use on them. But some of the examples can be difficult, so let's get some more practice right now. Here's the problem. Which method should we use? This one has several layers of fractions, so the method of fraction rules is probably best. Notice that we'll start where the fractions are buried the deepest, at the bottom there. The same way that you simplify brackets by starting on the inside. So we take the bottom of our fraction and get this subtraction problem. We start by getting equivalent fractions with a common denominator. We combine the terms, and then we put that answer back into our problem on the bottom of the big fraction where it came from in the first place. Now we've got 2 divided by a fraction, so we invert and multiply. We're dividing by 15 plus 2x over 5 plus x, so that's what we invert. It's getting simpler, so let's keep going. Finally, we have 1 and a fraction to add together. 15 plus 2x is the common denominator this time. we get an equivalent fraction for 1, 15 plus 2x over itself, and then we can add. Combine the numerators and keep the denominator the same. We've simplified our problem to one fraction. And then, be careful, you can't cancel anything. That's it. If you want more information, you'll find it in your textbook. And you'll want to do more problems yourself right away. As you work on them, try both the fraction rule method and the multiplying method and see if you get the same answer both ways. You should, of course. Now, to finish up, here's an application that uses complex fractions. Suppose you have an electric circuit with two capacitors, one after the other, like this. Then the formula for their combined effect looks like this. You can calculate how to replace them with a single capacitor. But if you think about it, you might be able to make the formula a little simpler. Try it now. Make the formula as simple as possible and then come back. I've seen two ways to do this, and I can use either one. I decide to use fraction rules first. So I start by adding the two fractions in the denominator. To do that, I find the LCD, which is xy. Then I make two equivalent fractions and add these two new fractions together. Then I'm ready to substitute that answer back into the original problem. That gives me 1 divided by a fraction. So I invert and multiply, and I have my answer. If you chose to do the problem by method number 2, and if you thought it looked a lot easier that way, you're right. Multiplying top and bottom by xy should help a lot, and it turns out to work much faster, too. That's why you want to practice both methods. Sometimes one is better, sometimes the other. But now you'll have both in your toolkit whenever you need them. Get some more practice now, and good luck.